13.1 Properties of Matter. So we are really finishing up talking about energy and everything that is related to matter. Chapters 14 and on, we're going to start talking about what we kind of light, sound, wave properties, electricity, and magnetism for the rest of the year after that. So this is our last chapter dealing with talking about matter, solids, liquids, and gases, energy, masses, and whatnot. So when we talk about matter, we can talk about pressure. Now, pressure usually applies to a fluid when we are talking about it from a physics standpoint. And a fluid is anything that flows. So if if it flows, it's a fluid. Can air flow? Yes. So therefore, air is a fluid. What else? Can oxygen gas flow? Yes. Mostly any liquid or gas can flow if it has no definite shape. So any liquid or gas is defined as a fluid. When we talk about fluids, we can talk about pressure. Pressure is a force on a surface. What is pressure equal to? Pressure is equal to force divided by area. Now, for those students in advanced chemistry, the difference between physics and chemistry is when we talk about pressure, in chemistry we like dealing with atmospheres or torrs, and in physics we like dealing with pascals. So pressure is equal to force divided by area. Pressure is in pascals, force is in newtons, and area is in meters squared. Now, advanced chem students, you're very familiar with this. There are multiple units of pressure. We use pressure for atmospheres. We have it for millimeters of mercury. We have it in bar. We can have it in torr, which isn't up here. We have it in pascals, and we can have it in kilopascals. Every one of those 5 units on the bottom is equal to one another. So 1 atmosphere equals 760 millimeters mercury. 1 atmosphere equals 101,300 pascals. When you convert, you're going to have to do a dimensional analysis or railroad track problems to solve. Now, also when we talk about that, you need to square your meters when converting. Your area needs to be in meters squared. So in the next problem here, we're going to deal with an example in which we need to convert from centimeters to meters, and we'll talk about what exactly we have to do there. So with that, we can talk in an example. Mr. Dick just bought his new Jordans for officiating basketball. They are his pride and joy. Some kid from Maple River offered him $150 to wear them for a game the other night. If Mr. Dick weighs 725 newtons and wears shoes that touch the ground over an area of 412 centimeters squared, what is the average pressure his shoes exert on the ground? So we're going to go through this. We know that force is equal to, pressure is equal to force divided by area. If we take a look at this, well, we don't know. We're trying to solve for pressure. The force that Mr. Dick is exerting is 725 newtons, and his area that he is exerting is 412 centimeters squared. However, what's important is we don't need that unit in centimeters squared. We need it in meters squared. So we're going to railroad track, and we're going to get rid of 1 centimeter to start. Centimeters, we're going to meters. We know that 1 meter, there's 100 centimeters. Well, we need to go square everything, so we're going to square the entire thing. So 1 meter squared is equal to 100 squared centimeters squared. So what we're going to do is we're going to square everything inside the 100 centimeters. So it's going to be 100 squared. So what we're going to do is we're going to take 412 divided by 100 squared, and that converts us to meters squared. When we do that, our answer ends up being 0.0412 meters squared. Go ahead and plug in what we have now. We know that pressure is equal to force divided by area. We know that the pressure exerted, we don't know the pressure exerted, so pressure is equal to the force, which is 725, divided by the area, 0.0412. And I made a typo or a miscalculation and multiplied rather than divide. So if you take 725 and you divide it by 0.0412. Your answer ends up being, with sig figs, 3 sig figs, our answer ends up being 17,600 pascals. If you have questions on the area, the conversion of area from centimeters squared to meters squared, we can talk about that in class. You just remember you have to really square everything. All right, so that is pressure. When we talk about pressure, we can study, for the most part, we've been studying solids and how they interact. Well, now we are going to study fluids. And when we study fluids or gases, there are really 4 laws that come into play when we talk about gases. Now, in chemistry, for those of you who took regular chemistry last year, you've already covered this. Boyle's law, P1V1 equals P2V2. P is pressure, V is volume. Charles' law, volume and temperature. V1 over T1 is equal to V2 over T2. Now, my personal preference is to cross multiply before I solve, so this equation could be written as V1 T2 equals V2 T1 if you wanted to start like that. V is volume, T is temperature. Our combined gas law relates all 3 of them. P1 V1 over T1 is equal to P2 V2 over T2. Again, you could cross multiply and get P1 V1 T2 is equal to P2 V2 T1. P is pressure, V is volume, T is temperature. Lastly, we talk about the ideal gas law. PV equals nRT. P is pressure, V is volume, N is the number of moles, and R is a constant. Now, advanced chemistry kids, this is where we have to pay particular attention to units. You've been using 0.0821 as your R value. The reason you've been doing that is because your pressure has been in atmospheres and your volume has been in liters. Now what you'll see is our pressure is in pascals and our our volume is in meters cubed. So 2 different units is going to change that number from 0.0821 to 8.31. So try and not get the 2 confused. So we have 4 equations. All 4 of these help us relate gases. So if we take a look at a multi-step example, a 20 meter cube sample of argon gas at a temperature of 273 K is at an atmospheric pressure of 101.3 kPa. The temperature of this gas is lowered to 120 K and the pressure is increased to 145 K. What's the new volume of argon gas? Well, the first things we want to do is figure out what we have. P1 is 101.3 kPa. Now, because these units are going to be canceling one another out initially in this step, there's no need to worry about what what unit it's in, long as they are in the same unit. So if both our pressures are in kPa, we're good to go. If both our volumes are in meters cubed, we're good to go. So we have V1 is equal to 20 meters cubed, and we have T1 is equal to 273 Kelvin. Likewise, we go and we look at our P2. Our P2 is 145 kPa. Pressures are the same units. Volume is what we're trying to solve for. And our temperature is lowered to 120 Kelvin. That should be V2 T2. So we go ahead and we look at the equation. We have all 3 constants. So we are going to use P1 V1 over T1 is equal to P2 V2 over T2. Now I'm going to cross multiply and rearrange before I even plug it in. So P1 V1 T2 is equal to P2 V2 T1. Let's go ahead and plug it in. Pressure, P1 is 101.3 times our volume 1, 20 meters cubed, times our temperature 2, which is 120, and that is equal to our pressure 2, 145, times our volume 2, times our T1, which is 273. We go ahead and we figure out our math for it. So we take 101.3 times 20 times 120, and we divide by 145, and we divide by 273, And we end up that our volume, our V2, ends up being 6.14. Sig figs is good. Our V1 was in meters cubed. Our V2 is in meters cubed. Next up, how many moles were in the initial sample of argon? Well, we're going to use what we already had. We had our initial sample P was 101.3, but remember, we're doing the mole equation. So we're going to have P, we're going to have V, we're going to have N, we're going to have R, we're going to have T. What's important is our R value is 8.31 pascals. So our 101.3 now needs to be 101,300 pascals. Our volume is good at meters cubed. It's 20.0. N is what we're solving for, and our temperature in the original sample was 273. So if we set it up, PV equals nRT. P ends up being 101,300. I apologize, I need to adjust my smartboard. V is 20.0. We're solving for N times 8.31 times T, which is 273. When you go ahead and do that, you end up getting, with 3 sig figs, N ends up being 893 moles of gas, or moles of argon. So what we end up having is we end up having 4 equations which can help us relate gases to one another using pressure, volume, temperature, and moles. A couple odds and ends. Pressure falling down on me. I won't sing that song again. Thermal expansion, just a general note on thermal expansion. Generally, when heated, all matter becomes less dense and expands to fill its space. What's the one exception to that rule that you can think of off the top of your head? Water. When water's heated, it takes up less space. When water cools, it expands. So that's the opposite. When we talk about convection current, that's the movement of fluids. So hot rises, cold sinks, such as weather patterns. And plasma, what is a plasma? A plasma is a gas-like state of negatively charged electrons, which would make sense. Electrons are negatively charged, and positively charged ions. So you have electrons and positively charged ions make up a plasma. Now, what is the difference between a gas and a plasma? The plasma has the ability to conduct electricity. So when we talk about plasma, where are some places in which we see plasma? Stars, lightning bolts, neon signs, fluorescent bulbs, TVs, all common examples excuse me, where you can see plasma. So we're really starting chapter 13. We're starting to study the phases of matter. Section 1 is on gases. 2 and 3 will be on liquids and solids. And we'll get a couple more equations dealing with each one. You guys will have a small problem set on this tomorrow. If you have questions in class, we can get them figured out.